In our next assignment, we are going to do this assignment in CAD, and we are going to do a tip-to-tail problem, and then a system here with a post and the cable and a weight. Let's think about that. In the first problem, he says, an eye bolt at A is in equilibrium under the action of the four forces shown. What does that mean? It means that if you put those four forces together tip to tail, they will form a closed loop, won't they? He says it's in equilibrium, so we've got equal and opposite forces and reactions, and we're going to have a closed loop. We're not looking for a resultant, we're looking for a closed loop. All right, and then he says, determine the magnitude and direction of P. Here is force P. So he tells us three of the forces, their magnitudes and their directions. The fourth force, we don't know what angle it is, and we don't know what magnitude it is. So we're trying to find both of those. Now this funny looking symbol under the arrow that looks like a ribbon, that is actually the Greek letter alpha, lowercase alpha. It's like our lowercase letter A. He's made it he's a little casual there. He's made it a little bit squished, but that's angle alpha. All right, so what you should do is draw the three forces that you know at the right length, at the right angle, and put them together tip to tail, and then see what kind of arrow it will take to form a closed loop. Now I've given you the answer at the bottom of the slide, and what you might notice is that the answer does not look anything like what he has drawn here. Look at this. Well, here's the magnitude. That's fine, 92.62 pounds. But here's the angle, 241.15 degrees. So here's 180 degrees over here, the horizontal line on the left. 241 is even further below that. So it looks like our force P is actually starting at this center point here and pulling down and to the left. That's what direction P is going. And also let me say that you might get numbers that are slightly different from these. That's fine. You don't have to be exact. But if you're in the ballpark someplace, it's probably correct. So that's the first problem. For the second problem, first I want to look with you at an example that he puts in the textbook. This example is quite similar to your second homework problem. He has a 100-pound weight hanging from some cables, and the cables are attached here and there. And he gives us the angles of the cables. And he says, from there, find how big is the tension in each of those cables. All right, what do we do? Well, let's think about making a free body diagram at one point. And let's think about what you know about how to do that. Get out your imaginary paper towel tube and focus in on that one joint, joint B. Forget about the wall and the ceiling and everything else and the other cables that are not here. Just look at joint B. And when you do that, you can draw a free body diagram at B. And thinking about what's happening with the weight pulling down and the other cables pulling, you might recognize that it looks like every one of those three cables must be in tension. So that means those forces must be pulling away. They're pulling away, every one of them. So here is his free body diagram of the joint at B. You know the magnitude of the 100-pound force. You do not know the magnitude of the others, but you do know their angles. And so you could make a tip to tail by drawing the one you do know, and then in any order you want, remembering to keep tip and tail, tip and tail. What he did here was he headed off with AB in one direction at some long length, and then the slopey one, BC, is tip to tail at some long length, and wherever those lines intersect will tell you the magnitude of force AB and BC. He calls them CB. So there are the numbers. As soon as you have those numbers, go back and put those numbers onto your overall drawing. This is called a force summation diagram, where you have all of the forces, the cables and the weight. You don't have to show the wall and the ceiling, but show all the cables, and write those forces that you found right there on those cable members. This will become important when we are analyzing trusses in another week or two, because a truss, it's similar to this in that it has sloping bars, but there might be more bars than you see here. And if you make a force summation diagram as you go along, it is easier to keep track of which ones have you solved already and which ones do you still need to find. So, from this force summation diagram, we see we've got 3 of them solved already. We only need 2 more. And looking at that force summation diagram, we think, all right, where should we point our paper towel tube? It looks like joint C is going to let us solve the other 2 cables. So let's look at joint C with our imaginary paper towel tube. Again, just look inside that circle. Forget about everything around it. Just look at joint C. And when you do, you will be able to make a free body diagram as he did here. You'll recognize again that all those forces are in tension, so the arrows are all pulling away when we look at joint C through our tube. So the only one we know so far is that BC is 200 pounds. Let me back up. We know that BC is 200 pounds. See why it's good to write numbers on your summation diagram? All right, that one is 200. Okay, that one is 200. So here's your free body diagram with one of them 200. Now you can do tip to tail. This BC is 200 things long. CE, we don't know how long it is, but we know the angle, so we can put it tip to tail at some long length. And CD, we don't know how big it is, but we know it's horizontal, and so we can put it tip to tail. And we have those 3 forces chasing each other around in a closed loop. Now we can measure CE, and we can measure CD, and we'll know the magnitudes of those forces, and we can write those numbers on our force summation diagram as well. And now we're done. We've found all the forces. Up here at the top is a table. This is where the author of our book is showing us how he would find the answers using X and Y components, as you have done in some other exercises. So he's writing in here, well, I don't know the numbers yet, but I'm filling in what I do know. And he's showing you how he would solve it. He's also showing you another thing which is interesting. He said, what would happen if I guessed wrong about what direction these forces were going? What if I thought AB was in compression, and I made the arrow pointing towards, and even more so, the other one too. What if I got this one wrong? I thought BC was in compression, and I made its arrow pointing towards. The only one I got right was the weight pulling down. What would happen? Well, the world wouldn't end. What would happen is if you were using trig and using one of these tables to add up the x components and the y components, and you ran through the numbers, you would get the right answer, you'd get the right number, but you would get a negative sign with each number. And what that will tell you is that the numbers are right. When you get negative signs for the answer, that means your arrows were backwards. If you had used the tip to tail method with these arrows wrong, and I did that at the bottom of this slide down here. So here are the arrows pointing the wrong direction, and I tried to stick them together tip to tail, and I found there is no way to make them form a closed loop when they're pointing the wrong direction. So these guys are not in equilibrium. There is no closed loop possible, and so now I see, oh, I've got them in the wrong direction. I'd better fix them. And so I will try turning them around the other direction. And when I do, then I am able to put the 3 arrows tip to tail. Now let's look at the actual problem you'll be doing. It's this one, kind of similar. So here's a 200-pound weight. Oops, sorry, didn't mean to do that. Here's a 200-pound weight hanging down. That's what we know. For the others, we know the angles, we don't know the magnitudes. So think about which joint would you start with your imaginary paper towel tube. I hope that you would say joint D. You will focus in on joint D, and you will draw a free body diagram of joint D. And hopefully you'll be thinking, well, these cables are all in tension, so you're going to have 3 forces all pulling away from D. And once you do that, you will be able to figure out how big CD is and how big DE is. And you can then write those numbers on this force summation diagram. Once you know those forces, so now you'll know, now you'll know CD. So now which joint would be good to focus on? Well, you're probably thinking joint C, and you are right. Now that you know CD, you can look through your paper towel tube, look at joint C, and draw a free body diagram of that joint. Ignore the rest of it, just look at C. So this cable is in tension for sure. What do you think cable AC is doing? Do you think it's being pulled on? I think if you put your arm in there instead of that cable, I think your arm would feel pulled on. I think that's in tension. So it looks like at joint C, cable CD will pull away, and cable AC will pull away. And what about this bar BC? I'll bet that's feeling compression, so I bet you'll have an arrow pointing towards C right there. Now you have a free body diagram, and you can put those 3 forces tip to tail and solve the cable and the bar and write those on your force summation diagram. Make sure on your CAD drawing you have a free body diagram of each joint, joint D and joint C, a tip to tail for each of those joints, and a force summation diagram.